This is clear. And but this is equal to 0. So this sum here is equal to 0. The sum over every single differential surface here. Every single differential surface as a Hammond cycle is equal to 0. And I sum over 0 is against 0. Okay? So I'm left with the line integral around the perimeter, right? dqi, or just dq over t, okay? And it's equal to all this sum here, is that part, right? Of dqh I dqh is dq I over ti, right? Something over all on the Carnot cycle. This is equal to 0. For a reversible process. Okay. Except that we get the reversible process. Okay. And just as an aside, not exactly as an aside, but I'll talk about this later. If you have an irreversible process, right? Because in this case here, you use the second equation, right? Reversible, this is actually less than 0. Then what you have, let me just write it down here. And this integral here, q vertical over p is right, it's less than 0. Reversible 0, reversible less than 0. Okay? So what does this tell you? This tells you that the integral, does that look familiar? We talked about that in the past, right? Often. Just as an analogy, remember, if you have this equal to 0, then what do you have here? Didn't use a state function, right? And so you have a path from 1 to 2. Right? Then delta u, which is equal to either from 1 to 2 up to u, is equal to u2. Right? Okay? So to show that, just take that example, right? We have this dq over d is equal to 0. Right? Let's consider a cycle. From A to B, not a cycle, a path from A to B to path 1, right? C1, right? And another one, also from A to B, I call this path minus C2, right? Okay, but this is just a closed loop integral. Right? If I actually reverse the power C2, right? What I have here is then this integral dq over t is equal to 0, but this is equal to just an integral through curve C1 from A to B. This is just inside, by the way, of dq over t plus an integral from, in this case, actually from P to A, right? From P to A, okay, of call this minus C2. So this is actually C2 dq over P, that is equal to 0. a minus integral from A to B, okay, of dq over t, right? Right? Okay, through path C2. Okay, this is minus C2. That's it, right? This is minus. I should call this plus C2. And then this is minus C2. And then this is plus C2 again, right? This is minus sign. Therefore, an integral from A to B through path C1 dq over t is equal to integral through path C2 from A to B dq over t. Right? That this line integral is path dependent. This shows that the integral is path independent. Okay? So if that's the case, just like energy, then you can define a quantity, and this quantity is called entropy. Right? I can define an entropy of any point, say point P. Right? This is an indefinite integral from a reference point somewhere, right? That entropy equal to 0 or close to 0 of dq reversible over t, right? And this quantity is called entropy. Then the difference in entropy between 2 points from going from A to B is just SV minus SA, right? And this is an integral from A to B dq ref over t. Okay? And again, this is path independent. Right? Therefore, here S is a state function. Okay. S is a function of volume, temperature, number of particles, however you want to construct this. Question? Okay. Let's see. Divide it differentially, I write it as an integral over there, but to write it differentially, I have ds is equal to dq ref over t. Right? As promised, as we discussed earlier, from looking at just the Carnot cycle, looks like there is a concept quantity there. It turns out it does. There is a concept quantity. It's called this dq over t. Right? Okay. And I can rewrite this as a dq ref is equal to dTs. Okay. Again, as a state function, and from the first law, what does the first law tell you? U is equal to Q minus W dq, right, minus dw. Okay, and in this case then is equal to just TdS, right? For a particular reversible process, of course, minus dV. Is it clear so far? Question?
Is there a way for us to know if it's a reversible in terms of Q or not?
Say again.
If it's heat reversible or not, is there like properties for that we know to know or it's given?
I can understand the question.
Oh, is it like for the if it's reversible in terms of heat?
Yeah, we'll talk about it when it's irreversible, right? And then it becomes the equality becomes inequality. Let me just continue on this. This equation shows that the natural variable for u is actually not t and v, right? I always discussed this in the past, right? The natural variable for u is actually, u is an exact differential, right? U is TdS minus TdV, right? And every element here is a state function, volume, entropy, and u, right? But for the natural variable for u is actually S and V. Okay? And in this case here, temperature then is just u S, if we know how to evaluate S, of course, at constant volume. Okay? Now,
What do you mean by EQ reversible? And what's the difference?
you'll see what is the difference. But in this case here, it doesn't really matter, right? Because the first law value du is dq minus dw, right? And then for a particular process, you'll see later on, right? And there's all this confusion about reversible, irreversible, and once we, at the end of the day, everything will come clear, right? But if this is reversible, right, then du is just TdS minus dV, and everything is a state function here, right? Everything is defined